We will be presenting an LLM-driven adaptive robotic manipulation for complex task planning and execution. Previously, lots of projects have attempted to use natural language inputs into an LLM to have a robot execute novel tasks. We wanted to try to also implement something similar. We wanted to use an LLM as a high-level planner so that we could have a robot complete various manipulation tasks. And we decided to construct a kitchen environment where the robot has to interact with various components such as a fridge, microwave, drawers, etc., and have it complete various tasks such as sorting, stacking, or setting up a table. Our approach includes an LLM that's inputted data from 4 cameras. These include depth, segmented, and RGB images, as well as a task order, a list of objects that are in the scene, and various skills that the robot is capable of, such as finding, picking, or placing an object and/or closing drawers, and then a map from the objects to their IDs. And from there, you're able to have a natural language input to the LLM and have it execute a Python or output a Python code for the robot to execute.
So let's present some of our robotic skill functions. So the first one is pick, which basically takes the segmented and depth images to then compute the point cloud using the pinhole camera model. And then from that point cloud, we can generate some grasp candidates, either using a bounding box grasp, which we simply fit the point cloud with a box and then use that frame to come up with a grasp, or using the antipodal grasp, where we sample some antipodal points from that point cloud and then generate a grasp accordingly. And then we take some of these grasps and then check if they are feasible. And if they are, we come up with a sequence of waypoints that allow us to grasp the object. Next function is place, which basically allows us to take an object and place it either in or on another object. We define some desired grasp positions earlier. So for example, for the drawer, it's above it and so on. And then we use these desired positions to do inverse kinematics and then motion planning. Next, we have open close, which is used to open and close fridges and drawers. So for these, we start by getting the handle location through the point cloud, which we approximate using the segmented images and the depth images. And then we use the predefined grasp orientations and translations that we know based on the joints behavior of these objects. And then we use these transformations to do inverse kinematics and then trajectory generation.
We had various scenarios to test out in the kitchen environment for the manipulator to complete tasks such as clearing the kitchen, organizing fruit, stacking groceries, and setting a table.
Let's take a look at the success rates of our pipeline in these scenarios. So we observe that as the tasks become harder, the success rate decays. And that was not the LLM was not the reason to that, since the code generated was very correct as we inspected it. But the main failure modes were these two. So one of them was the perception issues, since once we grasp the object, we have some of the point cloud which is occluded, and then we don't have a very good estimate of the center of the object. Another issue is a hardware issue, since we can see here the drawer opening up after being closed, and this might be a reason in the physical parameters of the object.
For the future, it'd be interesting to explore a mobile manipulator, perhaps even more cameras throughout the environment, such as the one in the gripper for better perception, and a larger dictionary of some fundamental functions that the LLM can reference. Thank you.